That one ended rather abruptly. Let's see. Go to where we were. We were talking about conjugate bases and acids. And we had covered this one. The phosphoric acid is dissolved in water. What conjugate acid is formed? And the conjugate acid there would be this one right here. 21 is B. 22, the answer is A. Okay. Here, 23, the answer is C. And 24, the answer is A. So here, if you have it going from increasing basicity, so this is the most basic one right here, what that means is that this is going to be the least acidic. This will be the least basic here. That means this will be the most acidic here, okay, when you have it combined with that H plus ion, okay. So this, many of you got right. I think everybody got that one right. But this one, most people got wrong. And it's the reverse order. So remember that. If you're going increasing basicity here, you've got to flip it around to get to increasing acidity here. Okay? Next, 25. That is B. 26 is A. 27 is B. And people did fairly well on all of those. 28 is C. 29 is A. Okay. 30 is A. Yes. The pH of the solution is, that actually should be 0.1. Let me see, where is it? What is the pH of the HI? Oh, yes. Okay. Negative 0.23 and negative 0.10. Okay. What happens is the pH is the negative log of something, okay? And so that's the reason why the negative signs are involved there. Usually it doesn't work out that way, okay? Usually I would have accepted B as the answer there instead, because it just doesn't. It's not a useful concept to have negative numbers for pH. 31 is B. 32 is A. Now several of you got that 32 wrong as well. And here what you have to use if you've got an NaOH here, to titrate that to find out what it is, use a standard solution of the opposite type, right? So if you have a base here, you use an acid to titrate it, where you know the concentration of this, and that will give you that value, right? You can't titrate this with this. It doesn't work out. All you're doing is just adding more OH ions to the solution. 33 is C. 34 is B. Several of you were thinking that was this number down here, okay? But when you have this molarity of a solution, what you're doing is you're taking the log of this number right here, okay? So it's going to be 2 decimal places over. So that means a -2. That means you're starting off from a 2 and you're subtracting the log of 1.4, right? And so the log of 1.4 is 0.1. And so -2 minus 0.1 gives you 1.9. Okay, that's how that's calculated. Review that calculation. pH of deionized water, 35. Everybody got that one right. That is A. 36. Again, this is 0.32. Okay. Several of you had the negative number on there, but the pH of this solution is 0.32. 37, the answer is B. 38, the answer is C. Okay, and then 34, this right here was obtained from the book. It's a value that they have published there, but it's good to know what the blood is a buffered solution and what the relative range of the pH of blood should be. And that is A, 7.35 to 7.45. Lower acetic acid, well, the higher the molarity is, the higher your acetic acid concentration. That would be A for 40. For 41, it's 1.25. This has the highest hydrogen ion concentration. This right here, this serves as the base, so the answer is C. 43, the answer is B. 44, A. 45, B. 46, A. 47, it is B. Okay, because the H2O doesn't enter into there because that's a pure liquid. Just like solids and liquids do not enter into these equilibrium expressions. So the answer 47 is B. 48 is A. 49, they just want you to know that 14 minus this right here will give you 12. And that's exactly what it is. So the answer is 49 is A. And everybody got that one right. 50 is B. Okay. And then this one right here, 51 is A. And 52 is C. Okay. Any questions on those? Don't hesitate to send me an email about them. Now let's go on to the problems. Again, mathematical equation for the reaction quotient, and it's the concentration of the reactants in the denominator, concentration of the products in the numerator, right? And as you see for this one, any coefficient, you just raise it to that number. So this is SO3, the product, raised to the second power. This reactant, raised to the second power. And this one raised to the first power. Just understand how you do those basically. The next one, what you had to do is you had to actually solve for that equation, right? First you set up this equation. So with this one, it's going to be the N2, that concentration, raised to the first power. This raised to the third power. And this right here in the denominator raised to the second power. And you can see that the N2, the nitrogen, is 0.15. This is 0.12. This is raised to the third power. And this is 0.50. And that's squared, raised to the second power, right? The answer, when you solve all of those, this cubed times this divided by this squared gives you 0.000864. Okay? So, the Kc, equilibrium constant for this is 17. This number is much smaller than 17, therefore the reaction goes to the right. This one right here. Here you've got another equation. You have to write this one out again. It's actually the inverse of this one up here, isn't it? So anyway, and all of these are 2 molar. But this is 2 molar squared. This is 2 molar squared. Those are going to cancel out. You're just going to be left with 2. So the Kc here is 0.23. That is less than this Q. So this is going to go to the left. Next, we have to do a concentration reaction, right? ionization constant for water at 60 degrees is this, okay? Normally it's 1 times 10 to the minus 14th, right? At 25 degrees centigrade. But raising the temperature also changes this ionization constant. Both your hydronium ion and your hydroxide ion are still going to be equivalent to each other. So that this equals one of those squared. So the concentration of this one is going to equal 3.05 times 10 to the minus 7th, right? And the difference between that and that's that concentration. That's going to the same concentration that you're going to have for this one. The pH is going to be 6.515, right? Minus the log of that concentration, okay? And this is how you work that out. Minus this log, minus log of 10 to this, whatever that number is here, gives you a whole integer, right? The whole integer 7. This right here is just the minus log of this, so the log of this with a minus sign in front of it ends up being 6.515. The pOH is just going to be 14 minus this number, okay? So this right here is the concentration for both the hydronium ion and the hydroxide ion. This is the pH, and the pOH, I didn't write it down here, but it's just 14 minus this right here, okay? So it's not going to be 7. It's going to be a little bit above 7. 7.48 is what it's going to be. Now this next one, nobody got this one right. Nobody. Okay? And it's for a couple of different reasons. First of all, on this one right here, what you were given is you were given the molecular formula, you were given the Ka, you were given the for the groups. This right here is irrelevant. You only need one of these to work with. And you needed the solubility coefficient, solubility of this material in water. What you were to do is to calculate, first of all, the molecular weight of this material. There's 7 carbons, 3 oxygens, 6 hydrogens. Total molecular weight, 138 grams per mole. If you've got 1.8 grams and that's the maximum you can get in there, but you divide this by the grams per mole and you get 0.0130 moles. Your Ka is going to be your hydronium ion concentration times your salicylate concentration divided by your salicylic acid concentration. This is X. This is X as well. This has to equal that. This is going to be this minus X. Okay, many of you, well, every single one of you who tried to solve it, tried to ignore that. It's not much smaller than this, okay? When you calculate it out, you'll see that you can't ignore that concentration. So you actually have to solve it using the quadratic equation, okay? So when you solve that quadratic equation, what happens is you end up with, this is 3.14 times 10 to the minus third. And so that means that this would have been right in this this place right here, right? So that's gonna definitely interact with that. Okay? So you cannot just ignore that. When you use the quadratic equation to solve it, you end up with an answer which many of you got, okay, of 2.50. But if you would have actually used your calculations and done the x squared, your pH would have been 2.45, not 2.50. That is a significant difference, and I did take off for that. Likewise, for this right here, your pH is 2.80, and there's two things here. Number one, on that one, you needed a different molecular weight, and you also could not ignore this quadratic equation. Those two things, so if you got this number right here, you essentially fudged it a bit, okay?